Today we're going to be looking at section 4.6, the second half of this, talking about half-life and decay. So radioactive decay is something that we look at a lot, and radioactive substances decay by spontaneously emitting radiation, and the rate of decay is proportional to the mass of the substance. So physicists express the rate of decay in terms of what we call a half-life. And half-life is the time it takes for a sample of the substance to decay to half of its original mass. So if we had something that was 100 milligrams, then basically its half-life would be the amount of time it takes for it to decay to the point of only having 50 milligrams left. So that's the half-life. And some things decay very rapidly, other things take a long time to decay. So for instance, here the half-life of radium-226 is 1600 years. So it's going to take 1600 years to go from 100 grams to 50 grams. So you can see that some things decay very, very slowly. So in general, we're going to use this formula here to model our radioactive decay. So the m of T is just going to be the mass that we have remaining after time T. M sub 0, like we said before, anything with a sub 0 indicates that it is your initial starting amount. Okay, so in this case, the initial mass. And then we're going to have 2 to the negative T over H. It's a negative because we are going to have decay, and therefore we're going to have this negative here. Because if you were to rewrite this, this would be the same thing as this. And if you recall, anytime our base is less than 1, then that would be decay. Okay, so H is going to represent our half-life, just like A represented our doubling time. T would be our time, and again, H and T have to be in the same units, so just be careful about that. Okay, so if we may also have to deal with relative decay rate. So we can easily find relative decay rate if you'll just remember this small formula here, and that is that the natural log of 2 divided by H is going to give you your R, or your relative decay rate. If you have your R, then you can represent it using this model here, which is your initial quantity times e to the negative R over negative R times T. Typically, mathematicians especially like to work with this natural log function, so it's going to be preferred in this form a little bit over this form as far as working with it. Okay, here we have polonium-210 has a half-life of 140 days. So this is going to represent our H in the formula. Suppose that a sample of this substance has a mass of 300 milligrams. So this is the mass that we're starting with, or our m sub 0. So we want to find a function m of T that's going to model the mass remaining after T days. So we know what the initial starting mass is. That's 300 milligrams. And then that's going to be times 2 to the negative T over, and the H would be 140. And this is a negative here. Okay, so negative T over 140. Okay, the next one, find a function using this model. So we're going to have m of T. We're still going to put 300 in for the initial starting value. We don't substitute anything in for the E. I need to figure out what the R is, and we said that R is the natural log of 2 divided by H. So that's going to be the natural log of 2 divided by 140. So when I do that calculation, I'm going to get R equals 0.00495. We are going to need to carry this to several decimal places, and it should specify in WebAssign exactly how many decimal places. So here I'm going to go back and I'm going to take this R and substitute it in here. So I'm going to have negative 0.00495 and leave the T in since it's our model here. So this is going to be the function that models the mass remaining after T days. Okay, find the mass remaining after 1 year. It really doesn't matter if you substitute into the first one or into the second one. Just because I think most people prefer the second one, I'm going to go ahead and substitute into this. Since T is represented in terms of days, instead of plugging in 1, I'm going to need to do 365 days instead. So I'm going to do 365. So 300 e to the negative 0.00. Multiply that by the t, which is 365. And so I'm going to get 81 point, no, sorry. I'm going to get 49.256 as my answer there. So that's the amount that's going to be left after 365 days. So we start with 300 milligrams and we have a half-life of 140 days. So after 140 days, we'd have 150 milligrams left. And then we want to go all the way to 365 days. So this looks like very much a reasonable answer we would expect for that amount of time to pass. Okay, part D, I'm going to go to where I have a little more room here. How long will it take for the sample to decay to a mass of 200 milligrams? So I'm going to go back to the model. Okay. So this represents the mass after a given time. So how long will it take for the sample to decay to a mass of 200 milligrams? So that's what we're going to put in here is our 200 milligrams. We started with a mass of 300. And we just need to find the t. So we'll start by dividing away the 300. So that's going to reduce to 2/3. Okay, we need to solve for the t, which means that we're going to need to be able to bring this down so it's not an exponent. We'll do that by using logarithms, and we're going to use a natural log because we have a base of e. So the natural log of 2/3 equals the natural log of e to this exponent. We know that those cancel. Okay, we want to divide by this. So we're going to get that t is approximately 81.9, and we're going to round that to 82 days. So this is the graph showing that we start with a initial quantity of 300 and we follow this decay model down, and you can kind of see the shape of that graph. Okay, here's another one very similar for you to try. So I would like for you to go through and try this and then check your answers. Okay, for this first one here, half-life of cesium-137 is 30 years, so this is our H. Suppose that we have 13 grams as a sample of 13 grams to start with, so that's our initial starting mass. So when we plug into this, we're going to have our initial starting mass times 2 to the negative t divided by 30. And we need to make note that our time is in years. Okay, so this will be the model that we would get. Okay, for the next one, we need to convert here. So we're going to need to know what our R is. And R is the natural log of 2 divided by H. So the natural log of 2 divided by 30. And that's going to give us 0.0231 because we want to round this to 4 decimal places. So now we're ready to put it into our equation. Our starting value is 13, and then we're going to have e to the negative 0.0231, and then we'll keep our t in there when we're talking about the model there. Okay, how much of the sample will remain after 74 years? So we're going to use our model, and I prefer to use the Part B model. Okay, so I want to know how much of the sample will remain after 74 years. So I'm going to plug this in for my t. So m of 74 is going to be 13 times e to the negative 0.0231 times 74. And when you evaluate that on your calculator, you are going to get approximately 2.4 for and that would be in terms of grams. Okay, last part here, after how many years, so that's our time, will only 2 grams of the sample remain. So this is going to be our m of t that we are given. So we're going to use that same model that we've been working with. I'm going to put 2 in. That's the amount that we have after a given time. And we've got to solve it for the t. Okay, so the first thing we want to do is get rid of the 13. So we'll have 2 over 13 equals e to the negative 0.0231 t. And so now this is just a regular equation. We'll need to take the natural log of both sides to cancel that e. Okay, so we're left with negative 0.0231 t, and that's going to be equal to the natural log of 2 over 13. We'll divide that Okay, so these are going to cancel. So t is going to be this expression here. I would wait to the very end before I put it all in my calculator because that way you don't introduce quite as much error with it. So when we put that in, we're going to have 81.03. This says round to the nearest whole number, so we're going to give 81 as our answer, and that's going to be in terms of years. Okay, here's one to practice with. So again, if you would pause the video and try this one, then we'll go over this together in a minute. So this problem is a little bit different. If 250 milligrams of a radioactive element decays to 220 milligrams in 36 hours, find the half-life of the element. So this one you're actually solving for H. If we look at this, we're going to go back, and I'm going to go back to the one of this form because I think that's going to be the easier one since it has the H in that formula, and that's what we're trying to find. So 250 milligrams is going to be our starting value, so that's going to go in here. The time that has elapsed is 36 hours. We don't know the half-life, so we're going to leave that there. And after 36 hours, we have 220 milligrams left. So we're ready to solve this equation. So I'm going to start by dividing by the 250. So this will give me 0.88. Okay, we're going to take the log of both sides. Okay, we're going to be able to bring this down. Okay, from here, the easier thing to do is going to be to cross multiply and then solve for H. So when I cross multiply, I'm going to multiply h. I'm going to have h times the log of 0.88. And that's going to be equal to negative 36 times the log of 2. We want to get h by itself, so I'm going to divide both sides by the log of 0.88. So h is going to be 195.2. And since we're asked to round this to our nearest whole number, we're going to give it as 195, in this case, hours, because that's what our time is measured in terms of. Okay, the last type of decay model that we're going to look at is Newton's law of cooling. And Newton's law of cooling states that the rate at which an object cools is proportional to the temperature difference between the object and its surroundings, provided that the temperature difference is not too large. So we've got a lot of different symbols, variables here that we need to talk about. So the D sub 0 is the difference between our initial temperature and our surrounding temperature, or between the object temperature. I'm very used to the sub-zero being the initial, between the object's initial temperature and its surrounding temperature. Okay, so the T sub 0 is that initial temperature of the object. T sub S is the surrounding temperature, and then the K is the constant that depends on the type of the object. For instance, some materials are going to cool more quickly and some more slowly, and so each different type of material is going to have a different constant. Okay, so here we have a cup of coffee that has a temperature of 200 degrees Fahrenheit is placed in a room that has a temperature of 70 degrees Fahrenheit. After 10 minutes, the temperature of the coffee is 150 degrees. We want to find a function that models the temperature of the coffee at time t. Okay, on this one, we're going to use the model for Newton's law of cooling, which, if you look back, is temperature at time t equals the surrounding temperature plus the difference in the temperatures times e to the negative kt. Okay, so when we look at this, what we know is that the surrounding temperature is placed into a room that has a temperature of 70 degrees, so that's our surrounding temperature. Our difference in temperature, if you recall, the difference in the temperature is the difference in from the object to the surroundings. So our object is the coffee, which is 200, and the surroundings is 70, so this is going to be 130. We don't know the K for coffee, so we're actually going to have to find that. And the way that we're going to find that is, we know this information that after 10 minutes the temperature of the coffee is 150 degrees. So after a time of 10, the coffee is going to be 150 degrees. So we're going to solve this equation for K, and that's going to give us that constant that we need. So the first thing we'll do is subtract 70. I'm going to divide by the 130. This will reduce to 8 over 13. Then I'm going to take the natural log of both sides. So I'll have negative 10k equals the natural log of 8 over 13. My last step is to divide by negative 10. So k is going to be, k is going to be 0.04855. So my model then is 70 plus 130 e to the 0.04855 t. That's going to be the model for the temperature at a given time after it has cooled. Okay, so find the temperature of the coffee after 15 minutes. So we're going to use this same model that we just got through constructing. So we're going to have 70 plus 130 e to the 0.04855 0.855T. And actually, looking back on that, that was supposed to have been a negative. It should have been a negative. Okay. All right, so to find the coffee after 15 minutes, I'm going to do T of 15. Okay, so that when I plug that in, plugging 15 in, I'm going to get 132.75 degrees, and we're going to report that as 133 degrees. Okay, after how long will the coffee have cooled to 100 degrees Fahrenheit? So we're going to go again back to this model. Okay, so we're asked to find how long, so that's our T. And this is the temperature after a given time. So that's going to go in here. So we're going to have 100 equals 70 plus 130 e to the negative 0.04855 T. First thing we want to do to solve this is subtract the 70. So I'm going to have 30 equals 130 e. Divide by the 130. So this will be 3 over 13. We're going to take the natural log of both sides. So these are going to cancel. So you can see that some of this becomes very much repetitive. The hard part is actually just knowing how to substitute all the information in. So we'll divide here. So we're going to get T is equal to 30.2, and that's going to be minutes. Okay, as far as illustrating by drawing a graph, you can do that on your calculator and just put the equation in, and you should be able to see what that should look like. Okay, this is the last one, so I want you to take a minute and see if you can figure this one out, and then we're going to go over it together. I wanted to include this problem because there again, a lot of times we think that the math that we're doing doesn't have practical applications, but if you are into forensics, basically forensics uses Newton's law of cooling a lot, and this being an example here, here we have Newton's law of cooling is used in homicide investigations to determine the time of death. The normal body temperature is 98.6 degrees. Immediately following death, the body begins to cool. It's been determined experimentally that the constant of Newton's law of cooling is approximately this. Assuming times measured in hours, suppose that the temperature of the surroundings is 70 degrees Fahrenheit. So that tells us the surrounding temperature is 70 degrees Fahrenheit, and we know the K is 0.1947. So knowing all of this, it makes building our model pretty easy. We've got to have the surrounding temperature plus the difference in the temperature. Okay, so our surrounding temperature, we're told, is 70 degrees. The difference in the temperature, so the body started out at 98.6. So the difference in the temperature between 98.6 and 71 degrees is going to be 27.6. The K is 0.1947. And then the time is the part that we're trying to find out. And we know that the temperature after this amount of time has decreased to 71 degrees. Okay, so we're ready to solve this. So kind of just to recap, we've got our surrounding temperature, our difference in the temperature between the body's original temperature and what it is now. So at this time now it's 71 degrees. So the difference between 98 98.6, and 71 is going to be this 27.6 degrees. And the current temperature is 71 degrees. So this is what we're left to solve here. If we look at solving this equation, I'm going to erase this so I can have just a little bit more space here. We're going to subtract the 70, which gives us 1 equals 27.6 e to this exponent. Divide by the 27.6. So we've got 1 over 27.6. And you could go ahead, since that's already a decimal, and convert that if you wanted to. All right, so now we want to get rid of the e, so we're going to take the natural log. Okay, so we'll have the natural log of 1 over 27.6 equals negative 0.1947 times t. Last thing we're going to divide here. And so one more time, we're going to have t equals, if I divide all of this out, then I'm going to have 17.04. So it looks like this person was killed approximately 17 hours ago. And so that's kind of how Newton's law of cooling is used to investigate homicides and determine time of death. Okay, so that takes us to the end of these decay functions and also to the end of what we're going to do out of chapter 4. So your next class will be a review day, and then you'll have your test coming up the following class day. So thank you and have a good day.